Yeah, so hi all, good evening and welcome back to the sixth week of TA live sessions for AI SMPS. Before we get started for today, can anyone confirm if my voice is audible and if the screen is visible?
Yeah, it's
Yes,
audible
please
on the
go ahead.
screen.
Okay, thanks for confirming. So, yeah, today we'll be discussing some questions from week 6 of the course. And I noticed that there were some requests for the specifically the SMGS problem. So we have a question based on SMGS in that in today's problem solving session as well, and I hope that will be helpful. So yes, without further ado, let's get started. So this is the first question in front of you. Okay. Um, the question tells us that we are given a map. Okay. S is the start node and G is the goal node, like in the previous cases also that we have observed, and the actual costs are given along the edges, and the grid in the background is again a 10 cross 10 grid, as we have seen in the previous examples in the previous live sessions. And what we have to decide is we have to see which of the two heuristic functions, Manhattan distance or Euclidean distance, whether they satisfy the monotone condition or not. Okay, that is the question. So I'll let this graph be here for a while. You can take your time to maybe you can take a couple of minutes to try to figure out whether Manhattan or Euclidean follow the monotone condition or not. Feel free to share your answers and then we can have a discussion on the solution. Okay, any guesses, any partial solutions? So do the
I think B is right.
okay, so we have one vote for option B. Um, what about the Euclidean distance? So the first two options correspond to Manhattan and one of them is correct. And similarly, one of C or C and D is correct. So let me do one thing. Let me try to write out what the monotone condition is, and maybe that will help refresh some ideas on what how to answer it with respect to the Euclidean distance. So let's say we have two nodes, okay, M and N in some graph, okay, and then we have a goal node here as well, but we are not looking at that at the moment. The heuristic estimate corresponding to this node would be, let's say, hm, and that corresponding to this node would be, let's say, h of n. Okay, and let's say that the actual cost of going from m to n is denoted by this k m comma n. Okay, so what the monotone condition says is that the heuristic function of m minus the heuristic function of n should be less than or equal to the actual cost of going from m to n. Okay, this is the monotone condition, and with this in mind, I'll shift back to the graph. and I'll let you try to figure out. So for your ease, what I'll do is I'll maybe show you the pre-computed Manhattan and the Euclidean heuristic values as well, so that it's easier for you to decide which of them are following the monotone condition and which of them are not. To calculate the Euclidean distance, you can consider some point as the origin, okay, because here we are calculating the heuristic function with respect to the goal node. So you can think that the goal node has coordinates 0, 0, and then it will be just a normal x1 minus x2 whole squared plus y1 minus y2 whole squared, square root of the whole thing. Was I audible? I think I got disconnected for a while.
Yes, yes, you are audible.
Okay, great. Yeah, so I was just mentioning that to calculate the Euclidean distance, you can think of the goal node as as the origin, having coordinates 0, 0, and then you can calculate the Euclidean distance for all other vertices depending on what position, what x and y coordinate they are occupying. So here I have represented pre-computed Euclidean and Manhattan distances, and you can consider any two of these nodes and see whether they satisfy the monotone condition. In order for us to just prove whether the monotone condition is satisfied or not, it's easier to prove that it's not satisfied, right? Because we just have to find one case where it is not followed. So let's say in Manhattan, we consider, let's say, the node that has the heuristic cost of 170 and 110, right? So that would be this one and this one, right? So the difference between the heuristic estimates of these two nodes is 60, and the actual cost of going from one node to another is 55, which is violating the monotone condition. So Manhattan distance, we can prove right away that it's not following the monotone condition, whereas the Euclidean distance, if you notice, for each pair of nodes, it will be following the condition. So it will be faithful to the monotone condition as specified over here. So if we have a look at the solution, the correct options would be options B and C, which says that Manhattan distance heuristic function does not satisfy the monotone condition, whereas the Euclidean distance does. What will be the xy coordinates for any node other than G? So that will be, okay, maybe I can just show you a sample of that. Let's say this is your origin, okay, 0, 0. So anything to the left of it will have negative x values, right? So these positions will have negative x values. Anything above it will have positive y values. So this top right corner, this will have a coordinate of how much? 0, 1, right? 0, plus 1, because we are moving plus 1 direction in the positive y, in the upward direction. Similarly, if you go to this particular node, which has heuristic value 90.6, this will be defined by how much? Minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9, and then plus 1. Okay, so minus 9 comma plus 1 will be the coordinate of this particular node, and then you can just follow as a simple Euclidean distance formula. Okay, any more doubts there, or shall we move on to the next question? Okay,
No doubts.
okay, great. Then let's move on to the next question. So now we will be reusing the graph that we have used till now in many of the previous live sessions, and we will try to solve it using weighted A star, BFHS, which is breadth first heuristic search, beam search, and finally SMGS, which is sparse memory graph search, one by one. Okay, so this is the same graph that we have been using. The conditions still apply. We have to start from the start node, reach the goal node. The cost associated with the edges are the actual costs. Okay, whenever required, we have to assume that the heuristic function to be calculated will follow the Manhattan heuristic function, and the grids in the background, they are again 10 cross 10 units in size. Okay, and whenever we have to break a tie, we have to choose alphabetical order. Every condition that we discussed in the previous live session still hold in this graph. Okay, now moving on to the question. So here we have to first attempt the weighted A star, and we are given that the weight W is 3 in this case. So instead of having F equals to G plus H, we will have F equals to G plus W into H, where W is 3. Okay, and we have to report the 4th, 5th and 6th nodes that will be inspected or explored or refined by the WA star algorithm. Okay, so I will go back to this image where you can see the graph more clearly. I'll wait for a couple of minutes so that you can try to attempt to form the WA star search tree, and then we can have a discussion of the solution. In the meantime, please feel free to share your answers. Okay, I hope the grid is visible properly now. I just zoomed in a bit. Let me know if it's still not visible. I'll zoom in further. Heuristic is Manhattan. We have assumed that the heuristic will be Manhattan. So the W is 3. Okay, we have to use weight as 3 and then solve the weighted A star method. So maybe we can get started with the solution step by step, and then we can all see whether we are progressing in the correct direction or not. Okay, so I have the tree constructed with me, but let's reveal it step by step. Okay, so the first node that we will start with will always be the S node, right, which is what we see over here. This is the first node to be inspected, and it has a function f value of 480, which we get from um, true cost plus heuristic estimate, right, and this we multiply by 3, right. So the true cost is 0 plus, if I remember correctly, 160 was the heuristic value, right, associated with S. So that gives us 480. Okay, maybe I'll remove this initial part to avoid any confusion. Okay, so that's how we get S with cost 480, and S has 4 possible directions in which it could go. These are E, J, K and O, right, and each of these have their own associated F values calculated in a similar manner, and you can verify that the F value for E will be 550, 600 for J, 420 for K and 420 for O again, right. um, are you with me till this point?
Yes.
Okay, great then. So given these options, which node do you think will be explored next? I mean, the answer is provided over here, but what will be the rationale behind choosing K as the next node to be inspected?
You have to, if the weights are same alphabetically, the lower one, the first one which comes has to be picked up, and the lowest cost you pick it up, heuristic cost.
Exactly, that's perfect. So we choose the nodes with the lowest cost, right? And that is 420, but we see two of them have the cost 420, and then we go for the alphabetically node that appears in the first alphabetically, which is K, right? So we choose to expand K next, and then K has a couple of neighbors, right? Of course, this is in this version we won't write that K can go back to S, right? Because this is we don't allow that in A star. So the nodes that we could go to from K are F, H, L and Q, and again they have their own associated costs, right? Maybe I can show you the graph one more time. So for K, from K we can go to F, H, L and Q. Okay, and they have each of them have their own costs that we have calculated using this particular framework, right? And out of, so K was inspected. Next, the one that we would be inspecting would be the one with the lowest cost again, and that happens to be 350, right? So among E, J, O, F, H, L and Q, L has the lowest cost, and it doesn't have any competitor, no other node with the same cost as L. So we will simply choose to expand L next, right, and that will give us H with cost 440. Okay, now notice that there was one path from S to K to L, S to K to H with cost 450, right, and now we have found a path from S to K to L to H with cost 440. So this is where again preemptive pruning will appear, and this node will be closed off for any future considerations, right. And then the next node to be inspected would be the next least cost node, which would be Q with cost 390. So that will be expanded into um, R and W. Okay, and then we will proceed in the similar manner, right? R will be expanded next to add P, V and X, and then P will be expanded, and then finally when P expand P, we will also add G to the open list, and finally G will be reached. So this is the 3 A star search tree. Okay, I'll leave this on here so that you can go through it and convince yourself that this is in fact the correct search tree. And the question asked us the 4th, 5th and 6th nodes to be inspected by 3 A star. which happen to be Q, R, and P. Okay, so I'll let this be here for a while, and please feel free to ask me any doubts that you might have.
Can you please repeat the reason for the logic behind pruning?
Yeah, sure. So this will follow the similar logic to what we had seen in A star in the previous week, right? So let me erase things, okay, so that it's easier to follow. So consider that we have expanded our tree only up till this point, okay, so we can't see the things below this. Let me zoom in. Okay, so till now we have observed one way to reach H from S, okay, and that is following this path. Okay, and this has cost 450. Okay, now when we expand L, we find another way to reach H which follows this path, S, K, L, and then H, and this has cost 440, right? Now this tells us that there is already a path that follows this S to K to L to H with a lower cost than what we would have gotten had we
Your
expanded.
voice is breaking.
Okay, is it better now?
Yeah, it is shattering. Yeah.
I'm sorry, I think there's some network issue on my end. I hope it's better now. Any better now?
Yes.
Okay, great. So what I was saying is, once we find this 440 cost path, we know that there's no point expanding this 450 cost path anymore. So we will, in any future expansions, we will not consider this particular H.
Still it's breaking.
Okay, let me
The
try
voice is not
something.
clear.
Yeah.
Let me try
Yeah, it
something.
is breaking. There is a lag.
Is my voice better now? Hello? Can you hear me now?
So now it's fine.
Is my audio audible now?
Yes, sir.
Okay. Clear? No breaks and all, right?
Yes, sir.
Yeah, now it's fine.
Yes, sir.
Okay, great. Yeah, so let me go back to the tab. So what I was saying is, yeah, so basically we see that there's a lower cost path, right? So there's no point expanding this particular path anymore, because this will lead us to a higher cost than what we want. That is what we do in pruning essentially. Does that address your query?
So does that mean that the pruning is applicable only after level 3 or so? Like same goes in at level 1 also, na? Where
Yeah.
you have the nodes E, J, K, like considering K and then the next node which is L, which
Mm-hmm.
has a cost of 350. So the same pruning is applicable to E and J also, right?
If we find another path to E and J that has a lower cost, then we will prune that particular previous instance of E and J. Okay, so the pruning is not meant for pruning out all the particular paths.
Okay.
So what I mean to say is, so I think I get what you are saying. You are saying that because we got K as 420, let's say till this point, and 350 with L over here, right?
Right.
What is the point of even considering E, J, and rest of the things? You mean, right?
Yeah.
Yeah. So that is essentially just the way the algorithm is constructed. Maybe we won't find any path that is. I mean, actually, you never know, right? Because let's see. Um, okay, I have not shared this tab. Okay. Um, so basically, the idea behind pruning. Let me just go over that once. Let's say you have some path starting from the start node, some node, and then some node. Let's say this is called A. Okay, this has some cost X. Let's say you find another path to the same node, and this particular path has cost Y, right?
Okay.
And if
Okay.
Y is less than X,
Hmm.
then you say that I don't want to keep this particular path that had cost X in my memory anymore.
Okay.
That is the idea
Okay.
behind pruning, but it applies to the same node. Okay,
Hmm. Hmm.
so let's say
Agree.
if this was A, if two paths to A had different cost, we would keep the path having the least cost. But here,
Okay.
this is with respect to H, and these are E, J, and O. Yes, it might
Hmm.
be that E is after all not required further in the search because it has cost 550, and maybe later on it's not going to be very helpful, or it might also be helpful. We never know that. But the thing is that when we do the pruning with respect to a specific node. So just because we find a path cost with H440 doesn't, or with L350, doesn't allow us to remove E, J, and other nodes from the search.
Understand. So only those nodes which have multiple paths are eligible for pruning depending on the case, whatever
Exactly.
is the cost
Exactly.
factor.
Yes.
Yeah. Thank you.
Okay. Thanks for your question.
I have a question. In case of Q, the neighbors are 1 minute.
In case
Um,
of Q, the neighbors.
K, neighbors are K, R, W, O. In
Hmm.
that you have chosen R and W.
Hmm.
Why not O and K?
Because O is already in the open list, right?
Uh, okay.
Okay.
But 1 minute, one
Wait,
minute.
wait.
Why I ask this question means in case of K, you have the
Yeah. So here
E, F. Yeah.
the neighbors of Q are R and W, and O as well. Okay.
Yeah.
K is already in the closed list, so we don't need to worry about that. You are saying why not we have O over here?
Yeah. Yeah.
Okay. Uh-huh. Fair point. Let's see if that will have a different cost. So if we go from S to K to Q to O, we would have S to K 60, to Q would be um, 60 again, or 120, and then Q to O would be um,
170.
170, right? 170, and then plus the heuristic um, value of O, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 12. So 120 into 3. So that would make it 170 plus 360,
530.
530.
So since the value is more than 420, you are not showing it.
I think that is the reason. In any case, I think for the sake of completeness, they could have shown it. But yeah,
Yeah.
but because adding this we won't really prove anything else.
Okay.
Maybe that's why they didn't choose. They chose not to show this in the search tree. But yeah, for the sake of
Oh,
completeness, you can still draw it and have that in
we
the.
can show it as no. It is not wrong, right?
No, it's not wrong. But
Yeah.
just that. So technically, if you think about it, right, if you add this O node over here, this itself would get pruned, right? Because you
Yeah.
already have a
Yeah. Yeah.
path from S to O, which is with a lower cost. So adding and deleting at the same time probably might be the reason why we still haven't added that.
Okay.
Yeah, but thanks for noticing that and thanks for pointing that out. That's a good observation. Okay, so to address some of the queries in the chat, um, yeah, I think Dhruv also asked the same question or no? Why didn't we choose O as the next node after S? Because we are choosing the alphabetical order, so that's the reason. And then there's another question on whether we prune the nodes only after finding the path for the goal. No, not necessarily. We don't depend on the goal. We keep pruning as and when it happens. And then pruning means updating the node with a lesser cost. Not updating the node necessarily, updating the path to the node with a lesser cost. Okay. Okay. Any other doubts in this 3 A star or weighted A star question?
Like in a previous session, we used A star,
Mm-hmm.
and in that, S cost was 160.
Mm-hmm.
So in this, we multiplied that cost with 3.
Yes, because we use a weighted A star version of the method where weight is 3. That's why we multiply it with 3.
Okay, sir.
Right? We use this framework, right? F function is defined by the true cost plus the heuristic cost multiplied by the weight. Weight happens to be 3 in this case, so we get 480.
Okay, sir.
Okay. Anything else? Okay, maybe not. Then maybe we can move on to the next method. If there are any remaining doubts with respect to 3 A star, please let me know. We can have a discussion again. Okay, so the answer was that the 4th, 5th and 6th nodes to be inspected by WA star would be Q, R and P, as we saw. Okay, now coming to breadth first heuristic search. Okay, the difference between this and the breadth first search is that we have this upper bound as an extra information supplied to us. Okay, what this means is that, let me shift to the Jamboard. Let's say this is the start node, okay, and this is the goal node. Breadth first search usually explores the neighborhood, right? It keeps on exploring the neighborhood until unless it reaches the goal node, right? What we say is that we have limited resources, right? So we don't want to keep on exploring all these nodes throughout the neighborhood as and when we move away from the start node. So what we do is we set an upper bound. Okay, and we say that we will explore nodes only in that upper bound. So instead of exploring all these things, we will instead explore only these neighborhoods. So first we will go in this direction, and then this, then this, then this, and this, and then we will keep expanding until and unless we cross the goal node, right? And how do we decide this threshold? that is what is given by this u, which is the upper bound, and this can be calculated in a number of different ways. For this particular question, we are let us assume that some oracle or some external entity has supplied us this upper bound, and usually in the questions in this course they will also be supplied this whenever you want to solve breadth first heuristic search. Okay, so what you have to do is you have to proceed in similar way to what breadth first does, but you have to prune the new nodes that should be added to the open list based on their f values, which is similar to a star, which is f is equals to g plus h. We keep only the nodes that have f values less than the upper bound. Okay, that is the difference between breadth first and breadth first heuristic search. Okay, so this is breadth first combined with heuristic search, and we have to apply breadth first heuristic search to the same graph and list the 4th, 8th, 12th, 4th, 8th and 12th nodes that will be inspected by BFHs, and we also have to report their costs. Okay, so I'll wait for a couple of minutes so that you can try to solve this, and then we will have a look at the solution. Okay, so to address one question in the chat box, you will follow similar strategy to what you used in breadth first search. Okay, so once a node is in the open list, you don't have to worry about adding it again. If it is in the open list, you don't have to add it again from another node. Okay, but you only add a node in the data structure only if it satisfies the condition on whether it is greater, the f value is greater than or lower than the um, upper bound supplied to you. So no pruning is done in breadth first heuristic search. Okay, if that was another question. Okay, you just if a node is already present in the open list, you don't have to add it again. So the algorithm is just breadth first search with the extra condition that you add only certain specific nodes to the open list based on the upper bound condition given to us. Okay, let's try to solve it step by step. Okay, so the first node in the search tree will always be start node again, right? Start node, and the cost will be, the f value will be 160, right, which is f is equals to g plus h. G is 0, h is 160, so that will be the first node. And then we can go to 4 different nodes from S, which is E, J, K and O. Let's write those down. So we have E, we have J, K and then O. Okay, and the cost associated for each of them would be 210 and 220. Correct me if I'm making any mistakes. Okay, 180 and then 180. Okay, remember the f value being calculated again is with respect, is following the similar formula to what we do in A star. This is G plus H. Okay, now in breadth first we just keep exploring the neighborhood, right? So the easy way to say that the order in which the nodes will be refined would be S would be first, E would be refined second, J third, K fourth and O fifth, correct? And as and when we refine these nodes, we will keep adding its neighbors to the open list. Okay, so E will be refined next in second place, right? So the neighbors of E are
A, B.
S, yeah, A, B and S, right, and F.
Yeah.
S is already in the closed list, so we don't need to add it. A, B and F, we have to consider whether we want to add them or not. Okay, so let's have a look whether we should add them or not. Notice that all of these nodes that we have added till now, they have cost f lesser than the upper bound, which is 303 that is given to us. Let's for the time being add all of them, okay, and see what happens. So A, B and F. A has cost 350, B has cost 310 and F has cost 280. So here A and B both have cost greater than the upper bound, right? So these will not be added to our open list, so we can simply remove these. The only child of E will be F. Okay, and then in order of expansion, after we have expanded, after E we would expand J, K, O, and then we will go to the next level. So F will be the 6th node to be expanded, right? While expanding J again, we will follow a similar logic, right? The neighbors of J that we can add are A and N, right? both of them can be added because they are not in the open list. A though has the cost 310 and N has cost 230. So again N will be retained and A will not be added to the open list. Okay, and this is how we will proceed with the expansion. So let me share the fully drawn breadth first heuristic search tree, and this is how it will look like. So these dotted nodes over here, these are the ones basically that could have been the children, but they were not expanded here, or they were not added to the open list because they are not satisfying the upper bound condition. They are exceeding the upper bound. Okay, so I'll let this search tree be here so that you can have a look and convince yourselves. And I'll wait for a couple of minutes. In the meantime, I'll look at some questions in the chat. We are having some difficulties. Which method we need to add new node even though it is the open list, and which method we don't need to add. So I get your confusion, Vedo, if I can call you that. So the only way to get this confusion resolved is by practice. Okay, what you do is here if you see over here, right, we are taking this same graph and we have been applying all the different methods to this graph, right, starting from the very early methods, right.
Yes, sir.
So similarly you take some graph. Okay, you can start with a very simple graph as well, which is easier to for which it is easy to just solve it manually, right, and see what is the optimal path cost. You can even design a graph yourself and then apply all the methods one by one to see in which method you add nodes to the open list based on what condition, how do you remove elements from the closed list and all those things, right. So as you practice more and more, it will become more clarified to you as to which steps to follow in which method. Okay, that's the only way to kind of address this, because see how in literature how these different methods have been reported or published is that you have a starting method, a baseline, and then you suggest some small improvement over it, right, to address one of the shortcomings of that method. For example, with BFS and DFS you have some limitations, you overcome that using A star. A star itself has some limitations, you overcome that with weighted A star. That might have some other limitation that you overcome with breadth first heuristic search. None of these methods you can say that are always applicable to solve all problems in all cases. Depending on the problem and the context, you can choose to solve your search problem using one of these methods that is most applicable and most optimal for that particular case. And to do that, you will have to understand.
Okay, sir. I have one more doubt.
Yeah, go ahead.
Hello. Yes, sir. If we can say a node is inspected, that means the children's which is related to that parent is in open list or not yet generated, sir?
No, when we are inspecting a node, we are considering the neighborhood of that particular node and then looking at which of these neighborhoods can be added to the open list. Once we have added those children which can be added to the open list, then we will say that now this parent node has been inspected and it has been refined. Does that clarify?
Yes, sir.
Okay. So Nandana, to answer your question, yeah, we are not doing any pruning over here, like I said. From J, why did we again add A since A is already in the open list? Okay, let's have a look at that. So where is J? No, so J A is not in the open list. Please make a note that these dotted nodes are not the ones that are part of the open list. The dotted node indicates that this could have been a child of J, but it was not added, not considered because it is F, because its F value is greater than the upper bound, which is 303. Okay, this dotted node doesn't mean that it is part of the open list. So as of now, when we are expanding or refining J, A is still not a part of the open list. Okay.
That means we are not visiting A.
Yes, we have not visited A yet. We have not even added A to the open list yet.
No, but why have we calculated 310 value for A again? Because once we have done it for A and we got 350, we don't even need to touch A again, right? Because that is already in the list.
No, it's not in the list. So the 350 value we got was via the path SEA. Okay. That this particular A node, this contender is following this particular path. Okay. And here also it didn't satisfy the upper bound condition. So again in this particular instance also it was not added to the open list. When we expanded J, this instance of A was coming from SJ and then A, and then again it didn't satisfy the upper bound condition, so again it was not added. Maybe in some expansion A would have satisfied the condition. In that case we would add it to the open list.
Oh, okay. Got it. Thank you.
Okay.
I have a doubt. Via J, A310, is it correct? Can you check that number? I am getting 280.
Okay, let's have a look. So we are going via S, J and then A, right? So 30
Yeah,
plus
yeah.
60, which is 90, and then A has heuristic value how much? 1, 2, 3, 4,
It's
5,
correct.
6.
Plus 30, I have missed it.
Okay, okay, yeah, yeah. So S, J, A, right? So we have to consider that. Okay, so to answer a few more questions in the chat box. So how do we calculate F? It is calculated as G plus H. G is the actual cost of going from a node to an intermediate node, and H is the heuristic cost estimated with the intermediate node. For example, if let's say the SJA case itself, right, which one of your friends was pointing out. So the actual cost of going from S to A would following this path would be S to J, which has cost 30, and then J to A, which has cost 60. So 30 plus 60, 90 would be the G. Okay, and then H of A would be the heuristic value of associated with A, which is the Manhattan
That is
distance.
220.
That is 220. Okay, so 220 plus 90, that gives you 310. Okay, that is how you calculate F as G plus H. Okay, and then some other questions. Yes, they have mentioned that BFHS prunes new nodes having F values greater than or equal to U. So whichever nodes that have the F value greater than or equal to 303, those will be these kind of dotted nodes. Okay, they will not be added to the open list. Okay, in week 6 assignment group 2.2, BFHS does not add to the open the neighbors that are already in the open or closed. Yeah, this is similar to what breadth first search does, right? The plain breadth first search, BFS. That's
Agree,
what
but why do they say that it does not add to open the neighbors that are already in open or closed?
Yeah, because that's what BFS also does, right? When you already have a particular node in the open list, which means it is yet to be inspected, right? Um, there's no point adding it again, right? Because it will already be inspected in the queue structure. At some point it will be inspected, so we don't need to add it again. And we also don't need to add it if it is already in the closed list, because it means that it has already been inspected. Does that clarify your doubt? Am I audible? I think I again got disconnected.
You are audible. You just explain taking one example
Okay, let me try something.
in the open list. This cannot be added. And
Um, let's say this is the open list. Okay, let's say some hypothetical A, B, F. Let's say this is not related to the graph that we are discussing. Okay, this is some hypothetical stack. Sorry, hypothetical queue. This is the front of the queue, this is the rear of the queue. So we'll add elements from here, right, and you will pop elements from the front like a simple breadth first search, right? In breadth first search, what do you do? Once you have already added a particular node to the queue structure, this is already stored at some position in this queue, right? So eventually, as we keep on inspecting elements, things keep getting popped out from the front. There will be some point when A will come at the front and it will be popped out and it will be inspected. So if in some other instance, let's say via some other node, let's say some node X, if in the moveGen function we could reach A from X as well, we don't need to add A again to the queue because we would already have A in the at some position in the queue.
okay, so this as a node has to be visited. So it doesn't require that it has to be visited twice.
It doesn't have
Are
to
we
be
saying?
visited twice.
Hmm.
Yes, it has to
Okay.
be visited only once, and once it is added to the open list or closed list, we don't need to add it again to the queue.
Okay.
Okay, so breadth first heuristic search is just the same as breadth first search. The only extra filter that you apply is when you add nodes to the open list, you just make sure that the nodes that you are adding doesn't have f value greater than or equal to the upper bound supplied to us. That's the only extra filter that we add when we do breadth first heuristic search.
Thank you, sir.
Okay, thanks for your question. Any other doubts in this breadth first heuristic search?
Sir, in this goal we have not reached, right, sir?
Um, yeah, we have the last level has G, right? See the leaf node, one of the leaf nodes is G via the
Yes,
path.
sir, but value is greater than F, no?
No, U was 303, right? This is 300 is still less than U.
Okay, sir.
Okay.
One more query, like supposing that we, as per the ask, they ask us say second node and the third node visited, and according to that, say we had to expand up to the third level only,
Okay.
and we have not reached the goal node.
Mm-hmm.
Okay, so in that case, the path will be nil.
Which path?
I mean, the path to reach the goal node. If there is a question like estimate the cost of the path or what is the path, then that path that is traversed will be nil.
No, if the question has asked us to find the path to the goal node, then we have to solve it until we reach the goal node. Even though they have asked us to report only nodes that are inspected, let's say in the third or the fourth order.
But I remember in one of the example, I need to identify in one of the practice assignment, they have given it like that, where the answer path is nil. That is because the complete optimal path has not been searched, like in the number of layers that they have asked us to traverse through, that path is not achieved.
I see. I see. So towards the end of today's session, can you make remind me of this question and we can have a look at it once?
Sure, sure, yeah.
Okay. So Dhruv, similar thing. Maybe you can remind me for this question again for towards the end of the session today. Or maybe let's do one thing. No point waiting, because since we are already discussing breadth first heuristic search, why not just address it once and for all? So can you point me to the question that you were talking about?
I think you can proceed. Let me locate the question. I don't want to waste time. You proceed. I'll just put it in the space. Yeah.
Okay, no worries, no worries.
Thank you.
Okay. So going back to the question, it asked us the 4th, 8th and 12th nodes to be inspected, and as you can verify from the search tree that those would be K, H and T with costs 180, 270 and 300. Okay. Coming to beam search next. Okay, so you saw one instance of beam search that we discussed with respect to the SAT problem in one of the live sessions, right? Here you have to solve this particular graph using beam search, and again you are given that you can use H values to decide what nodes to include in your beam, and you're also given that your beam width is 2, which means that the best looking two nodes are expanded or retained at each level, irrespective of whether they are better than their parents or not. Okay, and we terminate the search method if the new layer is not better than the overall best node discovered so far. If we have similar costs, oops, I think I showed you the answer but it's okay. If the nodes carry the same cost, then we use alphabetical order to break ties, and we have to report what is the path found by beam search and what is the cost of the path found. Okay, so again I'll leave this on here for you to try to solve it. In the meantime, if you can locate the question from the previous BFHS query, sorry, please let me know.
Sure, sir.
Varisha, to answer your question, yes, if at the next level the same node seems to have a better seems to be the best looking node, you can include it in the beam width that you have. As in, you don't care about repetition in beam search.
I have pasted the question. Week 6 practice assignment beam search. Question number 4.
Okay. So it's a beam search question. So let's discuss this question in the that we are currently looking at, and then let's go to this one. Okay. Any partial solutions till now? Okay, maybe I'll wait for a minute or two more and then we can have a look at the solution. So Nandana, to answer your question, so at every level, we just blindly choose the two best looking possible solutions. If it happens that this node is being repeated and it is also the best looking solution, then we will go for that, but that is unlikely to occur, right? Because we have already considered it once in the previous iteration, and since it was not the best, we didn't choose it, right? So it's unlikely that it will appear again in the next few levels. So the thing is, we don't care about repetitions, but it's also a case that it's unlikely that they will appear again in the next few levels. If it does appear, it will probably follow a different path, right? So in that case, we can as well add them. So let's have a look. Okay, so like in any case, we start with the start node, right? And the heuristic value associated with it, which is 160. Okay, and the four children of S are E, J, K, and O, right? So as of now, I'm not drawing the children, I'm just noting them down. E has heuristic value 170, J has 190, K has 180, sorry 120, and O also has 120, right? So here the two best looking nodes are K and O, right?
Yes.
So in level 2, we will only have these two children. Okay, then what are the possible children of K? These are F with heuristic value 150, H with heuristic value 90, L with heuristic value 80, Q with heuristic value 90, and S with heuristic value 160, right? So see, this is the point I think some of you were asking about. S is appearing again, but it already has a worse heuristic value than what we got in the previous level, so it will never be selected, right? We also have to look at what are the possible children of O, which are N with heuristic value 160, Q with heuristic value 90. See, again Q is appearing twice, right? Because they are following different paths. This Q is via SK and then Q, and this Q is via SO and then Q. Then we have S again with heuristic value 160, and then we have U with heuristic value 150. So out of all these, which two are the best looking possible solutions? One is L, right, because this has 80 cost. And what could be the second part of the beam?
Sir, Q.
Q, but see, multiple of them have cost 90, right? Q also has cost 90. Yeah, H also has, and this Q also has. So we have to choose the one that appears alphabetically before, which is H. So both of these are children of K itself, not O. So none of the children of O are actually considered in the next steps. Okay, and then we will expand H and L. Okay, so the possible children of H are C with heuristic value 140. Then we have I with heuristic value 60, and then K with heuristic value 120, and L with heuristic value 80. Okay, and then the children of, okay, we have one more, which is M, right, with heuristic value 50. And then for L we have possible children H and K. H with heuristic value 90 and K with heuristic value 120. And out of these, the two best looking ones are M
and I.
and I, right? Both of these are children of H. And so we will expand these again. So the possible children of I are D with heuristic value 100, G with heuristic value 0, H with heuristic value 90, and M with heuristic value 50. And the possible children of M are H with heuristic value 90, I with heuristic value 60, and P with heuristic value
40.
40. So here, which two nodes will we choose?
Reach to the G0.
G will be one of them. What will be the other node in the beam? Because the
P.
beam size is, yeah, beam size is 2. So even though we have reached the goal node, we will still have another element in the beam, right? So this is the children of M, this is the children of I, and we have reached the goal node, so we stop the search. And this is what the beam search tree looks like. Okay, I have it drawn properly over here, so let me shift to that. Okay, any doubts in this question?
Excuse me, sir.
Yeah, please go ahead.
Sir, actually, I didn't able to understand how you have chosen the node. I joined the class late, so I'm not able to, get how you have chosen the node and how you're tracing the path also. I'm very sorry to ask this question, but sorry.
Okay, no worries. So what we are doing is we are trying to solve a basically we are given a graph, okay, we are given a start
Yes, sir.
node, we are
Yes,
trying
sir.
to reach the goal node via different search strategies. One of the search strategies that we are discussing currently is beam search, right?
Mhm.
When
Yes,
we
sir.
start with S, we look at all its neighbors, which happen to be E, J, K, and O, right?
Yes, sir.
We calculate the heuristic value for each of them, and as per beam search, given that beam width is 2, we choose the two best looking nodes at a
Sir,
particular
here,
level.
here is only my question. Beam width is 2.
Hmm.
Means what? We have to choose the best two nodes.
Yes, exactly. At each level, you have to choose two best nodes. If the beam width
If
was
it is
3,
if it asks 3, then we have to choose best 3, isn't
yes,
it?
exactly.
And so it can be a question that with the beam width 1 also.
It,
Beam with
yeah,
1 also.
I mean, yes, technically it can be, but the purpose of beam is to have at least, uh, I mean, yeah, beam width 1 can also be present, but it will be very similar to what we can say is greedy search. We just keep expanding the pathway that looks the most promising to you.
Okay, okay.
Yeah, that can also happen. Yeah, it can be a possibility, but usually beam search is applied with beam width greater than or equal to 2. But yeah, technically it can always happen.
Sir, just I want to ask what particularly beam is मतलब what we are want to say about the beam is तो मैं हिंदी में बोलूँ क्या मैं ये जानना चाह रही हूँ बीम से हम लोग क्या रिप्रेजेंट करें जैसे कि हमारा रेसिस्टिक वैल्यू होता है और एक पाथ का लेंथ होता है तो बीम्स में वी आर फाइंडिंग द पाथ और वी हैव टू गेट द नेबर मतलब neighborhood node that is only my confusion
Okay,
that's
so
why I'm not able to
you can think of beam as a window. Okay, if you, so
okay
for
sir.
more detailed discussion, you can even visit one of the previous live sessions where we discussed beam search for the SAT method, so sorry, the SAT problem. So essentially the thing is, if you had expanded all of these nodes, right, your
Okay, sir.
search method would have been computationally very costly, right?
Yes,
What beam
yes, sir.
search wants us to do is we want to choose two best looking nodes so that we don't have to worry about expanding E and J in the first level and then all these other nodes in the next few levels. So it's just a way to make the computational aspect of this search method a bit more efficient. It does not necessarily say that we will always reach the optima by this way. It might as well be the case that because we are greedily adding the two best looking nodes, we will get stuck and we will never reach the goal node. But this is a trade off we are willing to accept for computational efficiency gains.
Okay, sir. Thank you so much, sir.
Okay. To answer a few more questions in the chat. Okay, I think this is with respect to the practice question again, right? So okay, so we'll have a look at that.
See, why add S again?
Where are
Okay.
we have not added S again, right?
Okay, we not added, but why you are showing this? That's the.
This is one of the, like I said, right? Here, because it's an undirected graph that we are considering, technically we could go back to S from O. Let's say this path S to O to S, right? We can go back to S from O again, but that will
Yes.
not really lead us anywhere, right?
Okay.
That is
okay,
also what is uh, suggested by beam search, which greedily looks for the two best looking solutions.
Okay. Okay.
Right, that's why they are possibilities, but we are not considering that because that is not looking promising at this particular level.
Okay.
Yeah. Okay, so to address two more things before we move on to the next question. Beam is considering only H values. Yes, we are given in the question that we have to choose we have to define the beam or fill in the beam using the heuristic value alone and not the G values. If the question says otherwise, using some other specification, we can follow that. But heuristic seems to make more sense because actual cost is kind of blindsided, right? If we choose G values, that will be the actual cost, right? We don't, I mean, we will be looking just one step into the neighborhood, right? And heuristic value gives us an estimate of looking of how much could the cost be of reaching the goal node. Okay, that's why we usually consider heuristic values and not g values. Final path, I think it is also answered by one of your colleagues. Thanks, Hema. So the final path is s to k to h to I to g.
K to H.
S to k to h to I to g.
So one more question is with me. In the third selection, no, it is the heuristic value 120. That is, I think, O. You have not chosen any of the node. Why, sir?
In which selection, in which level of the tree? Can you point me to that?
In the second level, sir, after S1,
Hmm.
160, E, J, and K, there is one node connected to S, and that is O. Okay.
Yeah.
In the lower, that is the just a child of the O, there is
Hmm.
N, Q, S, and U.
Yeah.
So you have not chosen any of the node. Matlab none of the node is marked as a blue. Why, sir? Because none of them is less than 80 or.
Yeah, we have to choose the best looking at each level, right? Irrespective of which parent it comes from, because the best looking in this particular level are H and L, which are
Okay,
both
sir.
which both happen to be children of K. We don't consider any child of O.
So, at every label, we have to choose two best, isn't it, sir?
Two best amongst all the possibilities at that level.
Yes. Okay. Thank you so much, sir.
Yeah.
Thank you, sir.
Thank you for the clarification, because while solving, even I also did it the same way as she suggested. Like for each child node which is expanded, from that set I took two, and so the answers were different.
I see. I see. Yeah.
We did the collective set.
Yeah. So at each
Yeah.
level, irrespective of which parent the child is coming from, we have to choose the two best looking nodes.
Mm.
Yeah.
Thank you.
Ashwini, I think you have posted a question that SKL here, L is 80. I'm not sure I follow. You're talking about the fourth level of the tree, is it? Oh, the third level. Yeah. Yeah, L has heuristic cost 80. That's why we included that. And yeah, thanks for posting the final cost also. So if you just add up the cost of the path SKHIG, it will, I think, turn out to be 430 as is suggested by Hema over here in the chat box. Let's verify that. Oh, it happens to be 310. Did we miss something? So S to K, which is 60, then H is 120, so 180, then I, which is 240, and 240 plus 70, which is, yeah, it should be 310. Maybe something got missed.
Yeah, I made a mistake.
Okay, no worries. So any doubts about beam search before we move on to SMGS?
No, please go ahead.
Okay, great. Let's move on to SMGS then. Okay, maybe this is another question with respect to beam. So this just asks us, at the point when we reach the goal node, when the algorithm terminates, what is the other candidate in the beam? And as we saw, that happens to be P. Right, so P is the answer here. I hope there's no doubt over here. Moving on to SMGS, which is sparse memory graph search or smart memory graph search. Both can be used interchangeably. Okay, let me first try to give you some intuition before going into what the method actually is. Okay, let's say this was your start node. Okay, this is your goal node. You have expanded some neighborhoods. Okay, and you have reached a certain stage where you have some nodes in the open list. Okay, so let's say this is your open list. Okay, this has some nodes. Let's say this is one node, this is another node, this is another node, this is another node, this is another node, and these are all in the open list. Okay, whatever is within this narrow stream over here. Anything to the left of it, let's say you have already explored that. Okay, and this also contains a some set of nodes. This is one node here, 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 this, so on and so forth. Okay, let me use another color for this, and this part is yet unexplored. Okay, so that would make this part explode, right? And we have a specific name for the elements or nodes that are explored. Can anyone tell me what that is?
Closed.
Kernel.
Kernel is part of the closed. We'll arrive at that, but first all the nodes that have been expanded, those are closed, part of the closed list, right?
Yes. Yeah.
So all these are the closed list. Now we have been working with simple graphs in our examples, right? But let's say you have to apply this to a very large graph, right? Which has millions of nodes. You don't want to keep track of all the nodes you have explored throughout from the beginning, because that would increase the constraints in terms of the resources that you have, right? Let's say you have limited memory and you can't keep track of all the millions of nodes that you have already explored in the closed list. Let's say your memory allows you to store only some few, let's say 4 or 5 nodes at a time. Then what do? You have to choose a way to get rid of the nodes in the closed list that you don't require further immediately, let's say. Okay, so let us note down our problem that we have. We have a problem of storing the closed list, and to address that, the first thing that we do is we divide the closed list into two parts. Okay, one part is called boundary and the other part is called kernel. Okay, how do we include or exclude elements from these two sub parts of closed? These both are included in the closed list. Okay, so closed is equal to boundary plus kernel. But now let's have a look at how do we define boundary, how do we define kernel. So boundary list consists of all those nodes in the closed list that have at least one connection to the nodes in the open list. For example, this, and let's say this, or let me draw it properly. Okay, so this node, this node, this node, and this node, these will be part of our boundary, right, which have at least one connection to a node in the open list. This could also be there. Kernel would consist of those nodes in the closed list, all whose neighbors are also in the closed list. For example, let's say we have some node over here that is connected to this one, and this one. So it has three neighbors, this, and this. All the neighbors of this node are already in the closed list. So we will put this particular node into the kernel part of the closed list. Is this much clear till this point? Any doubts till now?
No, sir.
Okay, that's great then. So
Sir,
this,
I just want to say that
uh-huh.
in other word, we can say that now the nodes which are not connected to open list and it has been already explored, those will be in a closed list. We can say that.
Closed list consists of nodes that have been explored. That is the only definition. Closed consists of both boundary as well as kernel nodes.
Yes, sir. Yes, sir. And just want to say, in the other word, we can say about the kernel that having no connection with the open list. Just I want, just it is my thought. Can
Yes,
we say that?
yes, because if a node is in the kernel part of the closed list, all its
Mhm.
neighbors will also be in the closed list, so it will have no connection to the open list. That is correct.
Yeah, we can say that the closed list consists of two types node, one which having connection with the open list and one which having not a connection with the open list, isn't it?
Yes, that is correct.
And okay, thank you so much, sir.
Yeah, yeah. So that's how you demarcate boundary and kernel. Now we can be given a graph and we can have different limitations on the size of the kernel that we have. Okay, for that let's go back to the question that we had. So for this question, assume that the sparse memory graph search, sparse because we are choosing to store only a sparse representation of the graph that we have in the closed list. Okay, we are considering only the boundary ones, and the kernel is separately stored. Let's say in some other location, not in the RAM that you are using. Okay, some hard disk or something it is stored, which has higher storage. So let's say that we have enough memory to only hold 4 nodes in the kernel. So the size of the kernel is 4. Okay, we will always assume that S, the start node, will not be part of the kernel because it is never deleted. Okay, we never want to delete the start node, even though it has all neighbors. It might reach a stage where all the neighbors of the start node are also in the closed list. Ideally S should be in the kernel as per definition, but we will never put S in the kernel because we never want to get rid of the start node. Okay, so that is one rule that we have to follow, and then we have to proceed with the rest of the search. Okay, and keep on expanding nodes in the open. More nodes will move into the closed, so at every step the boundary and the kernel will get updated. Okay, as we inspect more and more nodes. What this question tells us that we have to list the nodes in the open after SMGS has inspected the 4th node. Okay, where S is the first node to be inspected, which is given, and the second part is list the nodes in the boundary after SMGS has inspected the 4th node, where S is the first node to be inspected. So is the question clear?
Yes.
Okay, great. Then let's try to solve it step by step. Okay, so give me a minute. Let us start with the start node. Okay, what are the neighbors of the start node? We have E, J, K and O, right?
Yeah.
So we'll note them down. I am trying to follow the relative position of these nodes in the original graph. Maybe I'll show the original graph to you once and then you can take a photo of it so that you can refer to it readily as and when we solve the SMGS. Okay, moving on to the whiteboard. E, J, K was somewhere over here and then O was somewhere over here. Okay, now let's follow a color coding. Okay, all the nodes that have been inspected, let's say we will highlight it with yellow. Increase the weight. So after we have explored S, this will be part of the closed list. Okay, let's also draw some edges back to the parent node. Okay, please don't confuse these edges with the direction in which you are moving. Okay, these are just indicators that the parent of this particular node is S. Okay, so parent of E is S, parent of K is S, so on and so forth. Okay, now we will follow the A star method to find out which node will be inspected next. Okay, so I have the A star search tree from the previous week prepared, right, so that you can readily reference it. So after S, which was the node to be inspected next?
K.
K, right? So now let's inspect K. What are the neighbors of K?
N. No.
F is one neighbor, right?
FLQ.
F. Oops. F. H is also-
FHLQ.
Okay. H.
Your screen is not.
Okay. Yeah.
Yes, please.
Thanks for pointing that out. And Q. Okay. And let's again draw the edges. And let's mark K to be visited. Okay, so this yellow already indicates the closed list, okay, and all the uncolored nodes are part of the open list as of now. Now as per A star, which is the node to be inspected next?
O.
O, right? So let's look at what are the neighbors of O. Let me erase these things. Those will be NU
Q.
and Q. Now notice that Q is already having a parent which is K. So we have to check whether some kind of okay, in the previous step itself we should have done the checking. Okay, let's do that. While we were inspecting K, we found one path for H, right? Or maybe not. Okay, never mind. I think we were moving correctly only. So first S was inspected, then K was inspected, and then O will be inspected. Okay, fine. Yeah, ignore what I was saying. So N and U will clearly have O as the parent. Whether we want to have Q as the parent or not, that we have to decide, right? Because Q already had a parent in K. So that we can decide via the A star search tree that we had. Here you can see that the path from S to O to Q has cost 200 and the path from S to K to Q is 210, right? So the path from S to K to Q is costlier, so we will change the parent of Q. It's equivalent of doing pruning. Do you follow what we are doing here?
Yes.
Yeah.
So we will make O the parent of Q. Okay, and then we will mark O as visited as well. Oops. Okay, what is the next node to be inspected as per A star?
L.
L, right, which is the fourth node to be inspected. So let's look at the neighbors of L. The only neighbors of L are K and H, correct? K is already in the closed list, so we don't need to worry about it. It's already expanded. H we have to check. Okay, we have to check whether we can keep the path S to K to H or we include the path S to K to L to H. And based on the A star search tree, which path do you think would be more efficient? Anyone?
L to H.
L2H, right? Because it has a cost 260, which is lesser than
Yes.
270, right? Which is what the cost from S to K to H. So we will change the parent of H as well. And we will make L the parent of H. And we will mark L as visited. Okay, now we have expanded 4 nodes. Okay, and this was one point in which the question was asked, right? If we revisit the question, list the nodes in the open after SMGS has inspected 4th node, and list the nodes in the boundary after the SMGS has inspected the 4th node. So let's have a look at that. So it's easy to say what are the nodes in the open list, right? What do you
Yes.
think will be the nodes in the open list?
E, F, H, J, N, Q, U.
Yes. So E, F, H, J, N, U, Q, all these will be in the open. Now we have to decide boundary and kernel. Okay, let's note down what are the nodes in the closed list. Those are S, K, O, and L. Now we have to define which of these will be in the boundary, which of these will be in the kernel. So are there any nodes in the closed list that whose all neighbors are also in the closed list?
No.
No, right? So the kernel in this case will be empty. Do you agree with me?
Can you repeat the statement, please?
Yeah. So the open part is clear, right? Now we
Yes,
have
sir.
we have to check which of the nodes in the closed list are going into boundary and which are going into kernel. Okay, in case this is getting confusing with, okay, let me write it down completely. So the 4 elements in the closed list are S, K, L, S, K, O and L, right? In that order we refined it. We have to decide which of these go into boundary and which of these go into kernel. Okay, now remember the question stated that the start node can never be part of the kernel. So without thinking we can put S in the boundary. Agree?
Yes, sir.
Okay, now we are left with K, O and L. Now what was the condition for us to check whether an element is in the kernel or not? When all its neighbors would also be in the closed list. Here K has one node F which is in the open list, so this can't be in the kernel, right? So Fk will be in the boundary. L also has H in the open, so L will also be in the boundary. O has 3 nodes in the open, so O will also be in the kernel, not sorry, O will also be in the boundary, not in the kernel. So S, K, O, L, all of these will be in the boundary. Kernel will be empty as of now, as of the 4th expansion that we have done. Clear?
Can I ask one question?
Yeah, yeah.
For suppose for L, there is no child node called H. Then can we say L is kernel?
Yes. if let's say this h was not here, if this h was invisible, let's say, or not present, then the only neighbor of L would be K, which is only in the closed list, right? And then we could put L in the kernel.
But in the practice assignment, it was different.
Okay, was it the same graph or different graph?
Different graph, different graph.
Okay, did you make sure that there are no other nodes to connected to L that are in the open?
First you finish this, later we'll go to there.
Sure. So as of now, this is clear, right?
Yes.
So this was until the 4 expansions. Now I have the SMGS formed for the next few expansions. Okay, so this is what we also drew. Okay, this the color coding might be slightly different. Okay, so S, K, O and L, these are in the boundary, which is marked blue. Kernel is supposed to be dark blue, but we don't have anything in the kernel as of now. And green nodes are the ones in the open list as of now. This is after 4 refinements. Let's say we do 8 refinements. Okay, and that's when we will reach this particular arrangement on the left side. Okay, here we have all the green nodes are again in the open. Okay, blue nodes are closed. Dark blue is supposed to be one node that has all its neighbor in the closed list. Here S has J, E, K, O as the only neighbors that are part of the closed list, but we said that S can never be part of the kernel. So here also kernel will be empty because S will always go into the boundary. Do you agree with me?
Yes, sir.
Okay, so that was for the 8 refinements. For the 12 refinement case, now you have some contenders for the kernel, specifically K, L and O, because both all 3 of these, K has neighbors which are S, F, H and L. All of these are in the closed list, so all the neighbors of K, even Q and H, they are also in the closed list, although Q and H are not connected, so we don't need to worry about them. So K is in the kernel in this case, L is also in the kernel, O is also in the kernel, and S will be in the boundary. S cannot be in the kernel, and rest are in the open list. So does that clarify how do we categorize nodes as kernel and boundary?
Yeah.
One more doubt.
Mm-hmm.
After yes, no, I mean, if S not having any open child nodes, then can it present S in boundary or no need to present in both?
No, S will, if S has some nodes that are open and connected to it, S will be in the boundary. I'm sorry, S. Yeah. So we are starting from S, right? So the moment we are expanding the neighbors of S, it will go into the closed list. Now the question is whether we put it in the boundary or kernel, right? That is the question, right? Yeah. So for that, you always put S in the boundary because we are making it clear in the question that S can never be part of the kernel.
No,
why
that's
your
not
mark come after
my
arrow
question.
T? Hello.
Just a minute. So Shiva, was your doubt clear or?
No. My question is, see in the example, that means either left side or right side. So yes, having all the nodes in the closed list.
Yes.
So how can we can keep it that in boundary?
That is what we are defining it to be. Kernel consists of all the nodes that have all neighbors in the closed list except for S. Even though S looks like it satisfies the condition for being in the kernel, we will never put it in the kernel because see what we are doing is in kernel we are keeping only those nodes that we don't have immediate need of. We always have immediate need of the start node because whenever we find the goal node, we need to construct the path from the start node to the goal node. That's why we will never put S in kernel. We will always put S in boundary, even though it doesn't have any connections to the open list. That is just a rule given to us, let's say. Does that clarify?
Yes, clarify, but same problem with the assignment problem, practice problem, sorry, practice problem, same.
Okay.
They're not mentioning the boundary again.
Okay. We can have a look at that.
Thank you.
Yeah. Before we move there, did you have a query? I think Chandrakanta.
Yes, I have a query, sir. So my query is that some arrows are marked in blue color and some of them are in green. Is there some specification to mark them? The
So
blue or green?
basically, an edge connected to an edge emanating from a closed node is blue, an edge coming out from a open node is green. Okay. Okay, so these are the questions from my side for today. We can go to the practice question doubts that you guys had one by one. Okay. So which was the first practice question that we needed to have a look at? Can you remind me?
Sir, I have a doubt regarding this topic. Can I ask now or can I ask later?
Regarding SMGS?
Yes, sir.
Yeah, please go ahead.
Sir, after some refinements, I'm still not reached my goal. Unfortunately, my kernel is full.
Okay.
Why? Because the capability is 4 closed nodes only, kernel capability, right? Then I need to move further step, that is further refinement.
Okay.
So now the previous one will be erased, right?
Yes, it will be replaced.
Can you illustrate that type of example, sir, if it is possible?
So essentially you can think of it this way. Elements are entering your kernel with a certain timestamp. Okay. Let's say there are 4 things in the kernel, A, B, C and D.
Okay.
Okay, let me move to the whiteboard. A was inserted before, let's say A and B were inserted before C and D. Okay, and this is the size of your kernel. So when let's say you have to include few more elements into your kernel, you will give first priority to remove to A and B because they have been existing in the kernel for longer.
Yes, sir.
Okay, that's how you will replace it.
Then after, if I erased A node, all the children's which is connected to, it is already closed now. Okay, sir, fine.
Yeah, it's already closed, so we don't have to worry about it.
Yes, sir.
Yeah. So it works like stack. It's like queue. First come, first serve.
Yeah, you can say that.
Okay.
I mean,
it's not exactly like queue, but by understanding we can.
Yeah, I mean you will remove elements that are older, basically.
Okay.
Will they mention refinements? Shyamala, yes. They will. The question will usually specify you have to refine up until at this point. Any other doubts that I left unsolved?
Can you please discuss that beam search, the cast nil one which I had posted?
Yeah, can you tell me
Yes.
which
Week
question?
6 practice problem on beam search.
This one, right?
Q4.
Is this graph, right?
Yes.
Okay. Question 4. What is the cost of the path found by beam search? This one?
The answer is given as null. Yeah.
Null. That might mean that beam search is not located a path to the goal node.
So that is with respect to the number of traversals that we have done or the refinements that we have done. we could not reach to the goal node, right?
Yes,
That's
yes.
what we mean to say.
Yes, yes. I think that's what the answer indicates, but we have to verify whether that is actually the case by constructing the beam search tree. So, in your solution, do you also reach a state where you can't reach the goal node after until termination of the method?
No, I could reach the goal node, but with respect to the number of nodes that are supposed to get traversed, so within that space I could not.
Okay. Does it specify anywhere that you have to traverse only some certain set of nodes?
Yeah, it is given at the top.
Can you point me to that position where
Yes.
it's here? It's given search with beam width equals 2. Select the best two nodes and layer. If it we expand if it is better than the previous layer.
Manhattan. Here they have not start not expanded this to. They have mentioned first layer and the second layer, and they have asked notes in the second layer in the question number 2, right?
Start node is added in the first layer. By expanding the first layer, the second layer is formed. What are the nodes in the second layer? Okay.
Yeah. And then they have asked what is the path found by the beam search.
Okay. So I think question 3 and 2 are independent of each other probably. So
But how
maybe
come the cast is coming out to be nil? If we just select the answers, the right answer, cast was coming out to be nil. So
let's solve it.
that's
Let's solve it. So we start from the start node. Can you tell me what was the heuristic value associated with S?
with
So it's 1, 2, 3, 4, 5, 6, 7, 8, 9,
it is
10,
12.
11, 12, right? And it's a 1
Yes.
by 1 grid, so 12 will be the cost. So S with 12, this is expanded, and what are the possibilities over here? From S we could go to
CHIK.
CHIK. Okay, fine. Let's note that
C
down.
is C is with cost 13.
1 3.
Yes. Yes.
H
9,
I
11,
11.
and K.
5.
K is 5.
Okay, so the two best looking here are H and K,
Right.
right? So these will be the second layer of the beam search, right? So let's try to
Hmm.
answer that.
That is correct.
Yes. Now let's continue the search and see whether we reach the goal node or not. So we have to we have
Children are C, D, F, and K.
of H, right?
Yes.
Yes, yes.
C, D,
DFK.
F, and K.
Okay.
What are the heuristic values?
13, 9, 6, 5.
And for K,
K, it
K.
is children are
5.
H and N.
H, and N.
N.
N, right? Or is it something else?
Yeah, yes, yes. H and N.
This would be 9, and for N,
N is 3.
3. Okay, so the two best looking ones are N,
N is, sorry, not 3, it is 6.
6. Okay.
F and K.
6. Yeah, so these two.
F and K.
Okay, so here we will expand this only if the next layer solution is better, right? Here
Yes.
both the solutions are not better than K. Okay,
Yeah.
wait, these are children of which one? H, right?
Yes, yes.
Yes.
Okay, fine. So these are already not better than the current beam value. One of the nodes in the beam value, which is f, but let's say that we still want to explore this further. What will be the children of f in this case? K will be same again, right? H and N.
K will be
Yes.
K will be HN only. Yeah.
F, what are the children of f possible?
B
F
H
is
J.
B D H J.
B, D,
H J.
J.
H, J.
Mm,
And what
Yeah.
are the
B is
heuristics?
10.
Okay,
D is 9. H is also 9.
okay.
And J is 2.
2.
Yes.
Okay, so here J looks promising and N looks
N
promising.
is.
So N I don't think we have to consider because N is a child of K, right? But
Right.
it's not better than K, which is 5. So this is where the problem is running into a contradiction, right? Even though F has a child J that is better or better solvable, we can't really expand it. So I think we need to check what is exactly the termination condition of beam search. That will clarify the doubt. Do you remember which week had the pseudocode to beam search? Or is it specified anywhere in this question?
No, the termination is not specified here.
In each layer, the best 2 nodes are retained and that layer is expanded if it is better than the previous layer. So here the doubt is, what do they mean by better? Is it better with respect to only one member of the beam or both members of the beam? That is the doubt I think that is being faced, right? Because if we just assume that irrespective of which parent the child is coming from, it should be better than both the elements of the beam, then at this stage itself we will stop, right? Because f and k both are not better than k. Are you following me?
Yes,
But
yes.
as per your last explanation, you said collectively we look at it and we look at the two best notes, right? In that level.
Yes, best nodes in, so these two f and k are definitely the two best nodes in this level, but we
Right.
also have to make sure that these two are better than this level.
Better than the previous level.
Yeah.
Right.
Now, what do they mean by better? Whether it is better than both K
That
and H?
it is improving or it is worsening.
Yeah. Improving also,
But
but improving with respect to both of them or one of them? That is the question that I am currently confused about. For that, I think it's better if we have a look at some pseudocode given so that we can resolve it. Let's see whether the lecture materials has that. Oh, it has its solution over here, right? It's the same graph, right? Can you verify this? Is it the same graph that was in the practice question?
Yes.
Okay, so we have the solution in the lecture material. Let's have a look at that. See, so they are stopping at the third level itself. Even though f and k have 6 and 5, which are the best looking things in this particular level, I think they mean to say that we will stop the beam search when at the best 2 looking at a particular level are worse than even one of the elements of the beam search of the beam in the previous level. So because here f and k are not improving over k in the second level, we stop the beam search over here itself. That's why we say that it hasn't reached the goal and the cost is null.
So is it mandatory thing or we have to depend on the question?
No, I think beam search only moves when when it looks at a improved solution in the next layer. So that is characteristic of the beam search itself, not necessarily the question.
Okay, okay.
Okay, you can also have a look at this trace that is given. Okay, and I think this is the solution of the next few questions, where you expand all layers irrespective of whether they are better or not, right? This is what we were also trying to do initially. So here we
Yes,
expand
yes.
f and k even though that is not necessarily improving over k, and there eventually you reach the goal node via some path.
Yes.
Okay, so does that address your
Thank you,
question?
sir. There is one more question over there which has been posted. That is week 6 practice WA star question number 3 and 4. The
Okay,
statement itself is little more cryptic to understand. Infinity and
practice question, which one? Example.
WA star practice question number 3.
Which of these? There are two of these over here.
The
Practice.
first one. First
Okay.
is Q3.
Question 3.
Yes, there are some infinity values and
A node starts out with a default f value of plus infinity, and then WA star assigns the first f value. Later it may revise the f value and may propagate the improvement. List the nodes whose cost was revised. List them in the revision order. The first node that was revised goes first, and so on. So I think this is just a cryptic way of saying listing the nodes that are getting pruned. Not necessarily pruned, improved by propagation improvement. So what this infinity essentially says is that when you instantiate the search tree, before calculating the function cost f cost, you just in the implementation, because you have to assign something to the variable when you write the code, right? You have to assign something to the cost associated with that variable corresponding to that node, right? So you just instantiate it with plus infinity, some large value, and then you assign it some value when you first calculate the f value of that node. Okay.
okay.
And
Okay.
let's say by propagation improvement, it happens that you find some alternate path to that node that has a lesser cost. Then you revise the cost associated with that node and the path associated with that node as well.
Okay.
Correct? So I think that is what they are asking, but you can try solving the whole thing using propagation improvement and verify that. Or even this would have solutions given in that lecture material, right?
Okay.
We can have a look at that as well. Is it this one only?
Let me see.
Is it the same graph?
Yeah, I'm just checking.
Okay. Yeah, it looks like the same graph.
Yes, it is.
Okay,
Same.
and the graph in example 2 is different, right? Just to be sure that we are not looking at the wrong solution. Let me make sure of that. Yeah, example 2 is different, so this is the correct solution. So we are starting with S with F36, then we move to CHIK. K is expanded next. Oh, here have they not shown the propagation improvement or something? Oh, they have, right? This n is no longer supposed to be explored once you reach this particular n, 34, right?
Yes, yes.
Any other instance of propagation improvement? I don't seem to see anything else. This you can verify later on, but let's have a
Yes.
look at the solution and check what is given there. let's say if we enter just n, does it categorize it as correct or not? Yeah, it's correct, right? So n was the only node that was defined by propagation improvement. That's what they're asking in this question.
Mm-hmm.
Okay.
The fourth one.
Fourth one is for the nodes listed in the previous question, list their first non-default f values. Okay, so that essentially means that before propagation improvement, what was the value, right?
Achha. Okay.
Let's check that also. That was 50 initially. So let's enter 50 here and see if it is correct. Yeah, that's what.
Okay.
Does that clarify?
Yeah, yeah. Thank you. And just one more.
Okay, sure. To answer question in the chat box, Dhruv, yes, it's highly recommended that you solve the practice assignments before attempting the graded assignments. Any other doubts?
So from where we can see the solution, sir? I just want that task.
For practice assignment, you just attempt it, and then at the bottom there is this button to check answers that will show whether the answer is correct or not. For the graded ones, you can't see the solution unless the deadline has passed.
Okay. For the practice test also, we can't able to see the solution.
Sorry?
For the practice, this one is for the practice note, sir. Evaluate. It is not a quiz, no. For that also, we are not able to see the solution.
No, for seeing the solution, you have to fill in at least one of the boxes and click on this check answers and submit. Then you will be able to see the solution.
Okay, so that will tell the score only, no? But how to know the answers?
Oh, you mean
Like I mean, the steps you can't get to see, na. We have
Yeah.
to ultimate. We can only these are only the answer keys that you can get to see,
Yeah,
not the
solution.
exact steps.
So some of the solutions I think we noticed in the lecture materials, right? So I am hoping that they would be available for all other practice assignments as well. Like when you go to lecture materials,
Okay, sir.
this had the solutions for the different, at least two of the practice assignments that we discussed. Those solutions were there. So I'm hopeful that the other methods will also have some, other questions will also have some solution. So if you're not checking the lecture material folders, again, highly encourage you to do so.
Okay, sir.
Okay.
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 Any other
So
questions?
does the beam search algo retain duplicate within a layer? It is true, right?
Within a layer.
Yeah, at a level, uh, given level, can you have duplicate nodes in a beam search algorithm?
Um,
Like it could be, say, n coming from another node, but 2n is there at the same level.
hmm.
That is allowed.
I mean, technically, it seems like it should be possible, but I'm just trying to think whether that can ever happen. Um, because see, if you want to see, one of the conditions for beam search is what, that you choose the two best looking nodes in the next layer, and you expand those only if you find that they are better than the two elements of the beam in the previous layer. And if you are choosing to repeat one of the nodes from the previous layer, okay, you mean that okay, let me draw something. Okay, you mean a case like this where, let's say, this is the first node, these are, let's say, two elements of the beam, and then these have a few possible children, let's say this, and these three are the possible children of this particular node. Let me draw dotted edges to indicate that. You mean to say, let's say this is also A and this is also A, something like that you mean, is it?
Yes, yes, yes.
And both, let's say, have the same cost 2 and 2. Well, technically that should be allowed, but yeah, it seems to me it should be allowed. But why don't you also verify this through Bhaskar and Sir once via the discussion forum?
Okay, it is one of the practice question, W6 practice question Q1, where the expected answer is given to be S only.
S only.
Yes.
Where is it?
Uh, W6 practice. It's a kind of MCQ, S, no,
Um, I
a
can't
beam
find
search
it.
related.
Oh, beam search related. Okay. This one? You mean the ninth
Can you
question?
go up? Can you go up?
It is the first question, I think.
Yeah.
This one?
Yes, yes.
Okay. Does beam search algorithm retain duplicate nodes that occur within a layer? What's the answer?
S is the correct answer.
Then yes, we can. This verifies that.
Okay. Okay. So just one last one. Can you just scroll down and for this last question answer,
Hmm.
I'm not getting the third node. What is given? I'm not getting that. Okay, the correct answer is HK, FK, JN, and GM.
This one.
Yes, but I'm not getting the JN. I'm not getting.
Let's have a look at the solution then, which is done for us. Is this graph only, right? This is, I suppose, following the expansion irrespective of whether it improves or not, right?
Acha, okay.
So S, then HK, then FK, then JN, then GM. Isn't that the case?
Yeah, JN and GM, that is the one. But in the answer, I think they have marked it as JK.
JK.
Hmm.
Okay. Okay, it's not even appearing in this layer.
Yes, that's what is. I think either it is an
Might be a typo then.
erroneous.
No, it's same, right? S, then HK. What is it? S. First is S, then HK, then FK, right?
Yes,
Then JN.
right. But in the expected answer choice, it is
No, it's
JK.
JN only, right? See?
It's showing correct.
JN.
Yeah.
Okay.
They
Oh,
maybe then
I
what?
marked it as JK, I think.
Okay, maybe it was K before they noticed it and updated it. I don't know.
Acha.
But now it's correct, right?
ठीक है.
Okay. Any other doubts?
Can we
Excuse
move
me,
on
Thank you so
to
much.
Yeah, no.
SMG's formula?
sir, I have a doubt regarding this tree only. Can you
One
solve this
second.
one, sir?
I think Shiva has been waiting for a long time, so maybe we can address his query first. What was your query, Shiva? Can you come again?
That SMG's problem.
SMG's problem, okay. Which
Yes.
one?
The first one.
Example 2.
No. Example number 1. That means number is not mentioned.
Okay, this one.
Yes.
Okay.
My query with 4 and 5.
List the nodes in the open after SMGS is inspected, the 6th node.
Yes.
Okay. Well, let's see if we have a solution for this as well. So this is A star. Okay, not given. W A star, beam search A star. Okay. So Bhaskaran sir has not given the solution for SMGS, which is the confusing question, right?
Yes.
Okay. So what was your doubt about the correct solution itself, or some specific point in the solution process?
I raised 2 points. That is, if for suppose a particular node in the closed node, if you don't any child node further, so can we take it as kernel or still it continue closed? That's my question.
Okay, so kernel and boundary both are closed. That is clarified first, right?
Hmm.
So your question is whether if a given node has all of its connection or neighbors which are also closed.
No,
Then
it is already in the closed,
hmm,
but you don't have any child nodes further.
okay, it's already in the closed. Yeah, I mean
And
it
no,
will
no,
be in the
no,
closed only when its neighbors are already.
yes,
Oh no
yes.
no no. So you mean to say it is in the closed list, which means it has been refined, and what about its neighbors?
Yes. Otherwise, you go back to your presentation. There I
Okay,
explained. I raised that question. I can
okay.
easily explain.
Um,
Presentation slide.
this one.
No, no, no. Where you draw the figure.
Um, somewhere over here.
Here. For example,
Hmm.
L don't have the H.
Okay, L doesn't have H, let's say.
Then in that case,
Hmm.
uh, uh,
But L still has
what,
K as
what
well.
would be the case? No,
L
what would be the case of L?
L still has a neighbor that is K, right? Which is in the closed
Mm-hmm.
list.
Yes, yes.
So L will be in the kernel in that case.
But in the fourth answer they are not given differently. They are given different answer. That's
Okay.
my note.
Okay. Um, do you have your partial solution?
Yes, yes.
Can you post it on the discussion forum? I think I'm already way beyond my time for today. I can try to solve it step by
Yes,
step
I
now, but
agree.
it will take another a few minutes or so, 10 minutes or 15 minutes.
No, no issue. I'll give the values. Just you can draw the figure.
Okay, sure. Um,
First starts with yes. Gold. Yes.
fine.
We have CHIK.
Okay. S would be closed now.
Yes. The values are C is 19.
No, values, you can just, I'll just trust that you
K
are
is
telling
21.
the correct order in which the nodes are inspected. You just tell me which are the nodes that we are inspecting next. So after this,
I is 17.
so I will be inspected next?
Yes, yes.
Okay, fine. So I will go into close next. What are the neighbors of I?
E, L, and O. E,
B or D?
E for elephant.
Okay, elephant. E and
L,
okay.
L.
Yeah,
And
N and E and L are the only two neighbors. Am I audible?
hello, am I audible?
Yeah, now you're audible.
See, N for Nagpur.
Okay, N. Anything else?
O. O.
Oh,
O is there.
fine.
Yes.
Okay. Which node will be inspected next then?
Next, we have to visit again C because C is 19.
C. Okay. And as of now, there are no propagation improvements happening, right? Hello?
Hello.
Yeah, I think your voice is breaking
My,
slightly.
my network is yes, my network is not good right now. Okay, next node is C. CADH.
ADH. Okay. So A and D, let me mark. Is H getting propagation improvement or is it remaining the same? You can even write in the chat box, Shiva, if it's not audible. Um, Shiva, can you hear me? Okay, let me refer to the A star search tree that is given in the solution and use that as a deciding factor.
Sir, can you give only one clarification?
Uh, yes. Okay, while you are waiting for Shiva, maybe yes. Let me go ahead.
Sir, in beam search,
Uh-huh.
we have already explored something,
Okay.
but we are adding that node in new layer
Hmm.
for another parent.
Hmm.
It is possible in beam search, sir.
If it is coming from another parent, yeah, that might be possible, yes.
Okay, sir. Actually, we thought that once it is closed, we can't add as a new node.
So beam search will always proceed in a greedy manner, okay, as long as the conditions mentioned by the question are specified, beam width specified, whether or not you can move to the next layer irrespective of or dependent on whether you improve in the next layer or not. All these things have to be taken care of. As long as these are maintained, you don't have to worry about which node, whether the nodes are being repeated or not.
Okay, sir.
Okay. Okay, so let's refer to the A star search tree over here. So the first node to be expanded was in fact S, and then we had CHIK, which CHIK, which we also saw here, which we also added here. Then I was expanded next. Then we have E, L, N, and O, and the next element to be expanded was C, which 19, A, D, and H. So this gives a lesser cost for H. So H will be propagation improvement done. So the parent of H will change in the figure. Okay, what is the next node to be expanded? Let's have a look at that. The next node to be expanded is D, with which has only one child, which is F, with cost 22, and let's add that to our graph. Okay, next let's look at what are the node that will be expanded. Fifth node to be expanded is H, and no change happens, so we just mark it closed. Okay, this is what we did. Next node to be expanded is K. Okay, again no change happens. Okay, so we have expanded 6 nodes up until now. Okay, and let's go to the question that Shiva had asked. List the nodes in the open after SMJS has inspected the 6th node. So the nodes in the open list till now are which one? A, F, E, L, N and O, right? And you have to note them in the we have to write it in the alphabetical order. Yeah, can you please mute yourself? So we will have A, E, F, and what else is there? L and O. Let's check. Yes. Shiva, are you still there in the meeting?
Yes, my network is weak. That's why I'm not talking.
Okay.
I'm listening.
Does this clarify your doubt? This is the state after six refinements, right?
Okay.
So
what about the H and K? Are they in kernel or in closed?
H and K should be in the kernel. Have they not mentioned that it is in the kernel?
Please check in the next question.
List the nodes in the boundary after the SMJS has inspected the 6th node. Okay, fine. What will be the boundary? Boundary should be D, C, S will always be there. So S, C, D,
I.
and I.
Yes.
And they have mentioned H and K as well, is it?
Please check once. I think.
Okay. So we have to mention it in an alphabetical order, right? So it will be C, D, H, I, K, S, I suppose. No, H won't be there, right? C, D.
I. Yes.
C, D, I, S, yes. So they are marking it as wrong. They are calling H and K also. Can you raise this in the discussion forum? Based on my understanding,
Sure,
H and K should not be part of the boundary. It should be in the kernel. But let's get that verified from Bhaskaran sir.
Okay. And they go to see S is not there. S is hello.
Yeah. S is not here. That is also something that I don't understand. Can you ask that as well? It's more likely that Bhaskaran sir will respond with a answer if we give the partial solution. So you can even refer and say that we had the discussion in the live session and the recorded video will be available on YouTube. You can even refer to the video and the exact moment at which this discussion we are having in the video and say that, hey, we came up with this solution. Can you verify this? Because this is not in line with what we understand. Okay, including myself. I also, based on my understanding, H and K shouldn't be here, S should be here. I don't know if I am wrong, so it's better to get it verified from either Deepak sir or Bhaskaran sir. I think Bhaskaran sir is more likely to check the discussion forum.
Okay, sure.
Okay. Anything else?
Whatever question raised and the response given is sent only to the respective mail IDs or to everyone can see the response?
No, everyone who is part of the discussion forum can see the response. Ideally, that should be the case. I don't know how things are happening over there because I don't monitor the discussion forum that much. I only check it for queries about the live session.
Okay.
Yeah. But ideally, yeah, if a question is being asked in the discussion forum, the reply to that should be made publicly.
Is it so like that? Anyone can answer? Actually, I have not seen any response for the queries raised in the common forum.
Oh, yeah, anyone can answer to that, not just Bhaskaran sir. If it's
But
still not
some selected questions are answered by Bhaskaran sir. Not in every each and every question which is raised. Maybe
Yeah. Okay.
okay, I'll try to.
depending on the relevance, they pick and choose, and they answer only those like things which make sense, or maybe which are very important questions for which we do not know the answer, or it's not part of the content.
Ideally, that shouldn't be the case, but yeah, from my side, I can pass it on to the team. Um,
Hmm.
but yeah, unfortunately, that's the maximum I can do from my end. Um, yeah, hopefully there's someone will address it. Um, let's see what happens.
Hmm.
Okay. Thank you.
Thank you so much. It helped us a lot. Like we'll be able to solve the all the assignment questions now, I think, with the clarity that we have. Thank you
Okay,
so much. Yeah.
thank you for attending.
One more question from my side, sir. Sorry, sir, I'm sparing your time, but
Yeah,
still I want to know that. So
please go
there
ahead.
was one of beam search one and beam search two. Is both of them are different or same?
Where is it?
You can see in the beam search the practice session. No?
If it's mentioned beam search 1 and 2, it's probably defined in different ways. Probably one where we allow refinements.
I've seen that such question. The last where the ma'am was asking, no, can you open that? Go to the downs, at downs, downs. Uh,
Hmm. What is
like
part
what is
found
the
by beam search 2? Beam search
oh,
2
yes,
must be defined somewhere, right? This is beam
yes,
search 2, where we expand each new layer irrespective of how good or bad it is with respect to the current layer. In normal beam search, we don't allow expansion unless it is better, improving upon the current layer. Here they are saying expand irrespective of whether it's better than the current layer or not. That's how you get the second variant of beam search.
so we have to expand what the better two we will get, no?
Sorry.
Just according to that statement,
Hmm.
irrespective of the better two means it should be not be better than the previous one, but we have to expand, isn't it?
Yeah, it even if it's not better than the previous one, we still expand it. That's what it says.
Okay, sir. Okay.
Yeah.
Thank you so much, sir.
Anything else? Okay, if not, then let's end for today and let's meet next week. Thanks all for attending and see you next week.
Thank you so much, sir. Good
Thanks
night.
for your time.
Thank you.
Thank you.
Yeah.